I will be presenting results of hydrogen concentrations at the north pole of Mercury. And by measuring hydrogen, we can infer information about the water ice concentration at the poles of Mercury. And we use a technique that's called planetary neutron spectroscopy. And this is a technique that's been successfully used to measure hydrogen at the Moon, at Mars, and most recently at the asteroid Vesta as part of the Dawn mission. And what we do is we measure neutrons that are liberated off the surface of the planet by particles that are called galactic cosmic rays. And if I can have the first graphic, please. And cosmic rays, they're just very fast-moving protons that are flying throughout the solar system and the galaxy. And when they hit the surface of a planet like Mercury, they bust apart the atomic nuclei, and these nuclei contain neutrons. Can I have the next graphic? And so these neutrons, which are illustrated as the narrow yellow lines, they rattle around the surface, and some of them escape into space, at which time they can be detected by an instrument called a neutron spectrometer that's flying on board the MESENGER spacecraft. Now, if you happen to have a situation where a crater, say at the North Pole, as illustrated in this graphic, contains water ice, can I have the next graphic? It turns out that, of course, water ice is H2O, so it contains lots of hydrogen. Well, the hydrogen in the water ice stops the neutrons very quickly. And so the telltale signature, almost in a unique way that you would have enhanced hydrogen, is a decrease in the number of measured neutrons that you would see as you're flying over the crater. And so that's what we're looking for, is a decrease in the number of measured neutrons to tell us that there's enhanced hydrogen. Now, in the next set of graphics, I'll give a few words about how it is that we make this measurement on the MESENGER spacecraft. Can I have the next graphic? This is a perspective view of Mercury's North Pole, where we have these radar bright deposits discussed by Sean. And we can simulate what these would look like if you, say, put on neutron glasses, as it were. Can I have the next slide? And if your neutron glasses had perfect focus, this is the view that you would see. And again, where you have areas of enhanced hydrogen, you would see a decrease in the number of neutrons. Now, it turns out that planetary neutron spectrometers do not have perfect focus. They're, in fact, quite blurry. Can I have the next slide? This is what we would actually see when we're going over the Mercury's North Pole. We can't resolve individual craters spatially. Nonetheless, the telltale signature of hydrogen is still there if you have the enhanced hydrogen. And again, that's a decrease in the number of neutrons that you would see as you're flying over Mercury's North Pole. Now, what we can do is compare MESENGER neutron data with two hypotheses. And the two hypotheses are the following. One, that these radar bright regions contain very little to no water ice. The second hypothesis is that they are filled with water ice. Can I have the next graphic, please? And so what this shows is a plot of simulated neutron behavior, where on the vertical axis we have a quantity called relative flux. This is just a fancy name for number of neutrons that you detect for different latitudes that you would make the measurement at. And the latitude is shown on the horizontal axis, and the North Pole is towards the right. Now, the little to no water ice hypothesis is shown in the white line. And what you see is that the neutrons would show very little variation as you go from the equator towards the North Pole. In contrast, the lots of ice hypothesis, filling up these regions with pure ice, would be shown in the blue line. And again, as you approach these radar bright regions, if they contain enhanced hydrogen, you would see decreases in the number of neutrons. Next slide, please. And so now what we've done is superimposed MESENGER neutron data on top of those two simulations. And what we see very clearly is that the data track extraordinarily nicely with the simulation that says we have enhanced hydrogen. And so from these data, we can conclude, number one, there is certainly an enhanced hydrogen abundances at Mercury's North Pole. Secondly, it quantitatively agrees with the amount of hydrogen you get if these radar bright regions are filled with water ice. Finally, when we combine this neutron information with other information such as the radar data, the areas of permanent shade, we have very compelling evidence that these regions are indeed filled with water ice.